Hello, welcome to my space station. Today, let's continue our exploration of the realm of quantum physics and quantum mechanics. Today, we'll be delving into a topic called wave particle duality. Now, the first thing that comes into mind whenever I say wave particle duality is that there is something which is both a particle and a wave at the same time. So, let's understand this concept. This is a very fundamental concept in quantum mechanics, and a lot of the theories and a lot of the things that we have done so far would be impossible without this. For example, the quantum gates which were covered in my videos on quantum computing would not be possible if the electrons were not behaving like a wave. If the electrons were just a particle, then they would not have that properties which would allow them to move in a wave pattern which would allow the gates to work. That is why wave particle duality is such an important concept in quantum physics, and it's about time that we cover it. So, what's the difference between a particle and a wave? Now, these are two completely different things which, as far as the laws of quantum mechanics say, are fused into one. Now, first, let's understand what a particle is. Imagine a particle as a singular entity. It's just one thing. It can have motion, it can have spin, but overall, it does not have any more properties than that. Charge is something else. So, a particle is just a singular entity, while a wave is most often a particle which oscillates, which moves up and down, whether it be up and down in the sense of charge or up and down in the sense of motion. So, waves and particles are two completely different things. Now, a particle can just be a tiny ball, your ball can be a particle, and light can be your wave. But what quantum physics says is that everything around you is both a particle and a wave at the same time. Now, that seems very confusing, and that's something which it's pretty hard to believe. Like that's me saying that this table is a chair and a table at the same time. That does not make any sense. But actually, there is a lot of proof and there is a lot of research behind this. We have not just randomly said that okay, this pillow is a wave and a particle. No, there's proof behind it. Now, first of all, before we delve into the proof, there's one thing I need to clear is that uh, technically, even us humans behave like a wave for reasons we'll see later on, but it's very hard to prove that. For big objects and objects which are very fast, it's very hard to prove that. We will see that later on. So, there are two ways of proving this. Two very common ways are electron diffraction and the photoelectric effect. Let's first do electron diffraction. Now, diffraction is basically interference. Let's say you're in a wave, you're in a lake, right? And I throw two pebbles close to each other. Now, one very thing that we all know is that when you throw a pebble into a lake, there's these waves, circular waves that expand outwards. Now, if you throw two of them, there will be a point where these waves will interfere with each other. Now, that's just basically what diffraction is. In the sense of electrons, this is set up during as a very common experiment. We have an electron beam. We have a beam which is shooting electrons. Now, I won't go into the deeper working into this electron gun, but the concept is that there is a cathode on one side, the positive side, and the anode on one side. And because of the electrical difference, the electrons will try to move from the cathode to the anode as fast as they can. And this speed is just the electron gun. That's how basically they work. So by setting up an electron gun and by shooting electrons very fast across the space, you have a metal foil in the middle and you have a surface. It can be any surface, right? So now you're trying to detect the presence of electrons on that surface. Now let's first assume that the electron is a particle. If electron was a particle, then it would only go through one of the gaps of the metal foil. Now see, metal foil, right? There's metallic bonding in there. Now metallic bonding is just there are positive electrons, right? And then there are negative electrons. There are positive core and then negative electrons floating around in the sea of delocalized electrons. So there are just a few gaps between the sheets of the metal, and if the electron was just a particle, then that would just only go through one of the opening, and that would appear as one point, one concentrated point on that surface, right? But if electrons were a wave, that would mean that this wave would go through many different openings at once, so would not concentrate on one point. And when you perform this experiment, what happens is that there is one tiny point in the middle and there are circular rings around it. The picture would be shown on you, right? So what this proves is that this big point in the middle is the time where the electron acts as a particle, and these circular faint rings around that you see of electron presence is that electron acting like a wave as well. This is one proof that this electron is both acting as a wave and a particle at the same time. Now, we'll take another more interesting proof is the photoelectric effect. Now, the photoelectric effect is used in solar panels. That is, when photons strike it, there is an electron released by the metal on the photoelectric sheet, which the photons hit at. So first of all, we need to even prove that photons exist, because long ago, before Isaac Newton, people believed that light was just light. They believed that light could not be quantized. Now, what quantized means is to get something to its fundamental part. Let's take the example of a backpack. A backpack's fundamental part would be its books. There's no backpack without if you don't have your books in it, let's say. And then you can take the example of a fabric, the shirt that I'm wearing. The individual layers of fabric inside my shirt is just me quantizing my shirt. Obviously, the fabric can also be separated into atoms, but we'll go into that later. So basically, what people believed was that light cannot be quantized, light is just light. But then later, by the works of Albert Einstein, when he established the photoelectric effect, he also established the fact that light can be quantized, and the fundamental unit of light are these photons, these massless particles. Right? And he proved the existence of photons. But he said that photons only exist as particles. And he said that when a photon strikes the field, right, it strikes as a particle, not as a wave. Photons cannot exist as a wave. But then there was this tiny issue which this theory could not explain. The issue was that why does the energy of that photon depend on the electron output? If the energy is less, then we're not getting any electrons out, but if the energy is more, then we are. If the photons were just a particle, then that energy would not matter, but the energy does matter. So what's happening here? And then the works by many other scientists, right, later on, proved that first of all, we have to understand two equations. One, because when we start to understand the frequency and the amplitude of these waves, of these tiny particles, we cannot use our normal physics equations. So there are two equations. When you try to get the frequency, you can either do the Planck constant over the energy, or energy over Planck constant, or you can do the Planck's constant over the momentum of the particle. Now, when you use the first equation to try to describe this photoelectric effect, you see that the higher energy that there is, the more the frequency of the electron going in. That's assuming that the photon going in. That's assuming that the photon is a wave, right? And this can be explained because now you have energy into the picture, and that matches what we're observing. What we're observing is that higher energy, higher electron output, lower energy, lower electron output. And this equation, when you assume that this photon is a wave as well, explains this. That was one proof that photons also exist as a wave, but also exist as a particle, the particle duality of that. And then the second equation, which is Planck's constant over momentum, explains my second aspect, which the point which I said in the beginning of this video, that even though we humans also behave like waves, it's very hard to detect it, and yet it's very hard to prove it. So we all have a frequency, right? I am currently right now as a particle, and I'm also functioning as a wave right now. Thing is that my mass is so much that the frequency which is obtained by the h over momentum, because momentum is just mass times velocity, p is equal to mv. So my mass is so much, right, that the frequency is just, for all realistic purposes, it's just zero. You cannot detect it. And then it also applies to fast moving objects. Let's say I take a very, very lightweight object like an electron, but I shoot it very fast. mv, mass is the velocity is greater, that means the momentum by itself is also greater, meaning that this very fast electron will also have a very, very slow, very, very less frequency, and so it's very hard to detect it. That is why whenever you do these electron gun experiments, you try to make sure that it's the lightest particle, electron, and it's also not going way too fast. Sure, fast enough that it can penetrate the metal foil, but not that fast, else you will never detect it hitting the surface, right? So this is basically what wave particle duality is. All it tries to do is explain how everything is a wave and particle at the same time, and it applies to everything in this universe, even the massive thing, but just that it is very hard to detect it, right? And this was based on the works of Albert Einstein, Isaac Newton, and there were many other people like Hughes. There was a spacecraft named after him, and then there were many other physicists also involved in this. But the thing was that this laid the foundation of quantum mechanics, and this was the starting of the quantum revolution. After which we got ideas like the Schrodinger equation, which tries to describe the momentum and the wave function of an electron. Then we got this breakthrough aspect. Then we got the Dirac equations, which tries to describe the velocity of these for small fundamental particles, and the quantum physics field as a whole was built on top of this proof that everything is a wave and particle at the same time. So although this theory seems far-fetched and seems unbelievable, it is true, it's proven, and we just got to accept it at one day. So I hope you like this video and you learned a lot in this, and I'll see you again next time. Thank you.